Well, thanks. Thanks very much for inviting me out here. This has been a really fun trip. I've gotten to give a couple of talks already. I was out at Fermilab yesterday and went to an elementary school, and it's been fun to be out here. It's nice to be in cool weather. It was 100 degrees in California last week, and we were like saying, okay, we're ready for fall, and so it's nice to get out of there. My name is Steve Collins, and I'm an engineer at the Jet Propulsion Laboratory in Pasadena. I'm a spacecraft engineer. I've been working there for about 20 years, and I'm what you call an attitude control engineer. An attitude is the term that we use to refer to the orientation of the spacecraft. So my job is to keep the spacecraft pointed in the right direction, and I know all about the gyros and wheels and thrusters and stuff like that we use to keep the spacecraft oriented the right way. And I also do a lot of work with the navigation team when we need to correct the spacecraft trajectory. I help build the commands to fire the thrusters to correct the spacecraft trajectory. So I work real closely with the navigation team for all of that stuff. And on Mars Science Laboratory, I was responsible for basically flying the spacecraft to Mars and keeping the solar rays pointed at the sun and the antennas pointed at the Earth and that sort of stuff. So I'm going to talk to you today a little bit about the Mars Science Laboratory project. Before I do that, let me just give you a little biographical information. I started out as a hacker before there was really that term. I guess my first computer that I actually owned was a Commodore 64, and I taught myself how to program a Commodore 64 in BASIC originally, and then started learning, got a book and started learning machine language for the Commodore 64, and played around with doing computer graphics stuff. I was like, I really want to build like a simulation of the space shuttle, and started teaching myself how to do 3D graphics stuff. And, tried to do this space shuttle simulation and never got too far along. And then I learned Pascal. And when I went off to college, I ended up using the Commodore 64 to do, I have a bachelor's degree in physics and was always real interested in physics and math in high school. And when I went off to college, I ended up doing my bachelor's degree thesis on orbital mechanics, and I did all the orbital mechanics simulations on this Commodore 64. I also figured out how to use, hook it up. I wanted a letter quality printer, but I was too cheap to buy one. You could buy a dot matrix printer in those days, but like a letter quality printer, you couldn't really do. So I built a thing out of a drawer slide that the Commodore 64 would use the parallel port to control some motors and would drive a little carriage on this drawer slide and push the keys on an electric typewriter. And it would type like, 1 character a second or something. So it was not a very practical thing, but I found out in the process of building that how to interface motors to the computer and get the computer to drive it, and I need some sort of a sensor to tell myself what row of the electric typewriter I'm at, so I'm going to make a little cardboard thing that looks with a couple of, an LED and a phototransistor and make a little digital encoder and that sort of stuff. So all of that stuff, those kind of crazy things, you can just go buy now, those pieces for that stuff, and stepper motors and stepper motor drivers and all that stuff. And it's so wonderful to see you folks all playing with that stuff and learning to program, yourselves and fooling with Linux and all of that stuff. So I really come from this community that does that stuff, and I somehow magically found my way through that into the space business. Having learned to program in 6502 assembler enabled me, after I got out of school, to get a job with a little aerospace company that was writing software for an Apple II. Turns out the Apple II uses the same 6502 processor, and so that machine language that I learned on the Commodore 64 was usable for this software project. And this little company did also aerospace engineering. They were building an educational tool for to teach young people how to do simulations and stuff on the Apple II. And so they hired me, and I started, the minute I got in the door, started learning about aerospace engineering stuff and was interested in space stuff, so I soaked that all up. And at one point they needed somebody to go and go to Colorado to help support the launch of a spacecraft. And I said, well, I will do that. I'm the guy that will go do that. And so I ended up supporting the launch of 13 GPS spacecraft when they were first putting the GPS constellation up there. I don't know if you know that, right? GPS works with spacecraft. There's a whole constellation of, I don't know how many they have now. There's probably 50 GPS spacecraft up there, and they're up in orbits halfway up to geosynchronous orbit. And when they were first launching all those things, I worked on launching those, and that's how I sort of learned doing spacecraft operations. And then a few years later, I got a job at JPL working on a Mars mission. So let me start showing you guys some stuff about MSL now, but that's how I got to JPL. MSL is this giant rover the size of a car that we've sent to Mars to explore and look, try and understand the history of Mars, how the geology on Mars proceeded, where there was water in Mars's past, and look for places where it might be possible for life to have evolved or been preserved in the geology of Mars. Fossils of life there could be there if life evolved on Mars. There was a time period in Mars' early history where there was liquid water on the surface, and it's possible that life evolved on Mars and is still there, but had to kind of go underground because the conditions got more harsh. It's possible that life evolved on Mars and got transported to Earth on meteors. We get meteors on Earth that come from Mars, and there are also meteorites on Mars that come from Earth. There's a transfer of material both ways. When there's a big impact with either of the planets, it can throw stuff out away from the planet to escape velocity, and those things can wander around the solar system for a while and then go to the other planets. So it's possible life could have been transported either direction between Earth and Mars, and we eventually need to figure out how that all that played out in the early solar system. So we're going to fly our big Mars rover, and we're going to this place. This is called Gale Crater, and you can see the little landing ellipse there. This place is real interesting. There's a big mountain in the middle of Gale Crater, and that mountain, I'm sure you've seen pictures of craters on the moon. A lot of them have a central peak. Most of those are formed because it's sort of the splash, the frozen splash of the meteorite impact. Like when you throw a rock into a pond, a little jet of water will splash out of the center. And that happens with rock too, but this central mountain is not one of those, we believe. This central mountain has kind of a different character to it. If you look at it up close, and we can look at it from spacecraft that are in orbit around Mars, has a whole bunch of layers in it. It looks like the side of the Grand Canyon, actually. It's sedimentary layers. So what we think happened at Gale is that Gale was a meteorite impact, and it may have had a small central peak, but then it got filled in with sediments over the history of Mars. Water came in there, oceans came through there, and layered up lots of sedimentary layers. And then that all dried out, and then wind or maybe water then scoured out much of Gale Crater again, leaving this central peak that has all these interesting layers in it. And that's the stuff that we want to explore with the rover, because those layers, those sedimentary layers, let us basically go back in time. The oldest stuff is down on the bottom and the newer stuff's up on the top, and so you can just sort of read off the history of Mars by walking up the section with the rover. So how do we get there? We put the rover on a great big rocket. That's That's the biggest expendable launch vehicle that we have. And the rover folds up and goes in a little thing in the on the very top of that rocket, and that's kind of what it looks like in flight, folded up in there. You can see on the front there are solar panels. We get a lot of power from the solar panels during cruise, and the heat shield on the back, and then the rover is folded up inside there. That's sort of the stack of everything packed together. You also see in the middle there this thing that's called the descent stage, and that's sort of a rocket-powered helicopter that we use to lower the rover down onto the surface of Mars. During flight, let me just back up here, the spacecraft spins. It's spin stabilized during cruise. Some spacecraft are what we call three-axis, and they fire little thrusters or use reaction wheels to kind of stay in a fixed position. But this spacecraft spins like a top during cruise, and it turns out that's a real cool architecture to use for a spacecraft, because when you fire thrusters to control your attitude, it disturbs the trajectory a little bit. And this spacecraft only has to fire thrusters when we're turning or when we actually want to change the trajectory. And so it's real easy to navigate a spacecraft like this to Mars. There's, the corrections that you have to make are relatively small. Spacecraft spins at 2 RPM, which is kind of like this fast, which you think, well, that's not spinning very fast, but in space with no wind or anything blowing on it, that's enough that it is stable gyroscopically. And if you want to control the trajectory, we have a set of thrusters on each side of the spacecraft, and if we want to push the spacecraft sideways, we fire that set of thrusters, and then we wait until the spacecraft turns around here, and 15 seconds later we go and fire that set of thrusters, and that gives us a little push in this direction.
It's in space. If it weren't rotating, what would be destabilizing it?
If it weren't rotating and you just launched the thing with no control system at all, it would, solar pressure would, the sunlight shining on one side would, slowly start to make it turn. And it's important for us to keep it pointed in a controlled direction, because the solar panels need to stay pointed near the sun. And most, also important we have antennas on the spacecraft that we want to have pointed close to the Earth. And the spacecraft are typically designed to have one side kind of pointed toward the sun and one side that is designed to be on the cold side. So here's me in the clean room testing one of the sensors. That's the side of the cruise stage. On the side there, we're testing these sun sensors, which is you can see a little L-shaped slots in a little square box here. That's the sun sensor. And we're making sure that all the sun sensors work and are phased properly. It's real important that like when you guys build your first robots, you want, when you turn the joystick left, you want the robot to go left. And so you have to always make sure that the thing's all wired right so that it doesn't go right when you go left. And since spacecraft, you can't really fly the thing here on Earth, all that stuff has to be very carefully checked before you launch it. So phasing is super important for us. There's me standing next to the actual rover. We were in there testing. I just spent like a day or two in the clean room. It's not, there's people that specialize just in working in the clean room and assembling the spacecraft. You can see some of the detail on there. There's jillions and jillions of parts on there. Everything has to be assembled very, very carefully and kept clean, and no contamination and dust and fingerprints, and the wires have to not get pinched. And so it's real meticulous. It takes a lot of work to actually assemble the spacecraft, and people that are specialized in that do it. Yeah.
Just as part of your working life at JPL, I mean, your title was attitude control, so you were on the mission. Do a lot of people who work there, will they be in the clean room or looking at the actual space?
A relatively, there's probably 5,000 people that worked on the project, and probably 50 people or 100 people of those actually got to go in the clean room and get up close to the hardware. I actually never touched the spacecraft. You know, it's sort of because, you know, in order to touch the spacecraft, you need to have a wrist strap and be grounded and be careful that no static electricity is going to short anything out and stuff like that. And you don't want to leave your grimy fingerprints on the rover and stuff. And it's sort of like the spacecraft assembly guy's job to do the testing. And so we went in there to do this, to do the assembly. We went in there to do this testing, but we didn't, you know, like, I don't know, it would have seemed wrong to actually touch the spacecraft. I was really tempted to. It's like, it'd be really nice to touch the spacecraft, but I really shouldn't touch the spacecraft. So it's funny. But, you know, we all have our, like, signatures on a CD-ROM and stuff that are on there. But
How do you clear an entire room of dust?
the room has, like, air conditioning. The whole ceiling of it has filters and stuff in it, and it's the room is designed to be super clean. The air is in there is being constantly filtered, and people go through on a regular basis and just very carefully wipe down every surfaces where dust might settle. And so you know, and then the other thing is, people are incredibly dirty. I mean, they're constantly dropping hair and cells from their skin and stuff like that. And so that's why we're wearing the white suits, is to, you know, they're covering up our clothes and, you know, making sure that we don't drop anything on the spacecraft and stuff like that. And you wear gloves and you tape the gloves. And so it takes you about 20 minutes to get all suited up to go into the clean room. There's the inside of the rover. So it's, you know, looks like one of your robots out here. There's a lot of wires going everywhere. And a lot of people spend a lot of time figuring out how to plug everything together and make it work. Yeah?
What's the SAM?
The SAM. The SAM is the, Bill, maybe you remember, it's the SAM, it's the sample something. It's, yeah, there you go. That sounds great. It must be the sample analysis at Mars. There's science instruments in here that we can take powdered samples of soil or rock, you know, grindings, and put them into the rover through a little funnel, and it can do chemical analysis on them. There's a mass spectrometer and instruments that can tell, you know, the chemical composition of the samples, so that they use for geology.
Scientific analysis module?
No, it's a sample analysis of Mars.
Yeah, you know, a lot of these things are named with acronyms of various kinds, and they sort of get shorthand names, and you go, oh yeah, that's that. And I'm a little weaker on the science instruments than on the spacecraft engineering part, because you know, it's 5,000 people worked on this, and everybody has their specialization. I'm sorry, say again?
It's just thinking to be able to catch one of the engineering guys talking to it.
Oh, I mean, I think we talk to it. Yeah, I mean, we conceptually talk to it every time we send commands, and we, you know, I don't know. Yeah. Yeah, I mean, really, I should be talking to the descent stage, saying, you better work. That's the descent stage behind us there. That's me yelling at Fred. Fred wrote the software that controls the attitude of the vehicle when we're descending and landing on Mars. He's the guy that did all the radars locking on the ground, and I'm going to, you know, fly the spacecraft and touch down on Mars. That's the radar that you see, the thing that looks kind of like a surfboard in the front here, that has the different radar beams looking down. And I'm probably getting way behind here, so I'm going to speed up. There's a shot of the solar system, and that's the green line there is our trajectory that we took to Mars. The Earth and Mars have to be lined up in the right places for us to get there. So there's a launch window about every 2 years when you can launch to Mars with a rocket that you can afford to build. we launched the thing about a year ago. And you can see there's these things marked as TCMs on there with little arrows. Those are trajectory corrections. Usually flying to Mars, you design about 5 or 6 trajectory corrections on the way. You launch the vehicle actually not quite at Mars. You aim a little bit to the right so that the upper stage of the launch vehicle isn't going to hit Mars, because that's a big dirty thing that has birds in it and stuff from Florida that you don't want to accidentally fly and hit Mars. Where the spacecraft has been very meticulously cleaned and sterilized, their planetary protection guys say, no, don't launch direct to Mars. So TCM-1 makes a correction to our trajectory that takes us over to where now we're actually flying to Mars. And then the other trajectory corrections refine as we go along. We measure where the spacecraft is using Doppler signals of the radio link to the spacecraft. We figure out where the spacecraft is, and the navigators can know the spacecraft's position in the solar system to something like the size of a soccer field. And they, as we go along, we say, okay, we're going a little to the right, so make a little correction. The final corrections was just a few millimeters per second of delta V. So, so slow that you can almost not see it. Just a few seconds pulse with our thrusters. There's what it's kind of hard to see on this thing, but the green is the Doppler signature from one of these TCMs, and there's two events in there. You see where the wiggles up and down are kind of a signature for the spacecraft spinning, and then there's 2 burns that happened, and then the curvy part at the end is us actually turning the spacecraft to put it ahead of where the sun is. And we do that a few times and correct the trajectory to put us right in the exact spot that we need to be to land on Mars. And there's kind of a quick overview of all the stuff we need to do to land on Mars. The landing site is in Gale Crater. The different size ellipses that you see there, the largest one was the Viking lander. That was the target ellipse for the Viking lander. And you can see we're getting better and better. We can land in smaller and smaller places, which means we can go to more interesting places. Viking needed to find a big flat spot, the size of Gale Crater, that was safe for it to land. And now, since we can land in something that's just a kilometer across, we can actually put ourselves down on the floor of the crater and have a short drive to where the interesting geology is. So we hit the Martian atmosphere, and these thrusters on the descent stage, this is after we've dumped off my favorite part, which is the cruise stage, which I was testing in the high bay. Yeah?
What about the tungsten ballast rates?
We're just about to the tungsten ballast masses right now. So we dump off the cruise stage, which has the propulsion system for doing those trajectory corrections. And then we're about to hit the atmosphere here, and there's a set of 6 little circles here that have these things called balance masses. They're made of tungsten because tungsten's real dense. And we fire those off with little explosive charges. And that makes the spacecraft kind of shifts the center of mass. So when we hit the atmosphere, the spacecraft won't sit quite square. It has a little cant to it. And that cant makes some lift. And that lift lets us control the trajectory. If the spacecraft is going to land a little short, if the gyros and accelerometers, the IMU on the spacecraft, tells us we're going to land a little short, we say, oh, we want to go longer, so we turn the lift vector that this cant causes up. So the spacecraft stays in thin atmosphere for longer, which makes the spacecraft fly a little farther and land a little farther down track. And likewise, if we're going too long, we turn the lift vector down. We can also do a little cross-range control. The space shuttle does sort of a similar thing. This scheme was invented for Apollo. the Apollo capsules returning from the moon use this sort of guidance. And that lets us get that ellipse smaller. So we slow down with the atmosphere with the heat shield for a while. We drop out a parachute and we dump off the heat shield. And after we dump off the heat shield, the radar, which is on the front of the descent stage there, can now see the ground. And you know, we've so far from the top of the atmosphere down to here, we've been using this IMU, these gyros and accelerometers, much like there's a guy out here that has a quadcopter that has a little IMU in it. Same basic concept. It has a little rate sensor and some accelerometers, and it can, you know, stabilize the quadcopter. We have basically the same thing, but ours cost $1.5 million. And it was navigating us from the top of the atmosphere down to this point. Now we can see the ground. We turn on the radars, and the radar turned out locked up about 6 kilometers. When I play the movie in a second, you'll hear a call out for, you know, the radar locked on. And then it knows what our altitude is, and it corrects the altitude so that we can do the final touchdown and know where we're at.
What's the parachute made of?
The parachute's made of like regular old parachute-y stuff. It's, you know, nylon ripstop, you know. Yep, it's supersonic. This parachute is designed to work in a supersonic regime, and the cords for it, I think, maybe, you know, have Kevlar or some sort of aramid fiber in them, so they're really strong. But if you know, I've seen the parachute material, and it's, you know, looks like a parachute. It's the biggest supersonic parachute anybody's ever built. And it's, you know, of course, tricky to design a parachute to work in the supersonic regime. Yeah.
The lander is landing autonomously, right? It's not landing with human control?
That's right. There's not human control because there's like a 10-minute one-way light time. So, you know, it's all happened by the time we get a signal about it. So the whole entry, descent, and landing thing happens so quickly, and everything has to be autonomous for that.
How fast are you sampling your sensors, essentially, or your gyroscope? And how often do you make corrections?
It's the IMU, I think, was 100 hertz, so really fast. Or no, it was 64 hertz. And then the actual control loop is, you know, only firing thrusters probably, you know, at 8 hertz or something like that. So the IMU, the measuring stuff is happening much faster than the actuator stuff. Right. And the actuator stuff is set up to be relatively slow because the you know, there's structural modes and stuff in the rover. You know, if you try and do things too quickly, the rover or the descent stage actually will start to flex and stuff like that. So we descend on the parachute for a while. We drop out of the back shell, and there you see the rover is folded up and is underneath the descent stage, and we got these 8 MLE engines that come on and start slowing the rover down. And then after we've slowed down a bit, when we're getting down close to the ground, we actually lower the rover on a set of cords down below the descent stage so that we keep the rocket engines and stuff well up above the surface. And just before we touch down, we drop the landing gear, some pyro bolts fire, and we release the suspension, the wheels and stuff on the rover, and it falls into position. And then we fly this thing down to the ground, and it, you know, supposed to fly down like at 1 meter per second. I think we touched down at 0.6 meters per second. And when the rover actually touches down on the ground, the descent stage goes, oh, I suddenly got a lot lighter. And the engines throttle way down, you know, so that it can try and maintain this descent rate. And when that happens, it goes, oh, I must have set the rover down. I'm done. Pow, 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 fires a bunch of pyro bolts to cut the bridles that are holding the rover, and it says okay, and it uses a little it's not an Arduino, it's actually a Spark processor, but it's a little embedded computer on the descent stage to say, I'm going to just fly away now and go crash. And it goes and runs the engines for certain fixed times and then shuts them off and crashes, and you'll see the destruction that ensues from that.
Why didn't it just land? You had all the control to do that, right?
Well, we don't want the dirty, filthy, ugly rocket engines right next to the rover. We don't want it to land on top of the rover.
Fly away and land, not fly away and crash.
Oh, because there's nothing we're going to do with it. It's done. What's that? Yeah. Yeah, it's more stuff that it has to do. So we set the thing down, and then the thing flies away. So this is us in the control room before landing. You see Mohawk guy there, my pal on the left. He's one of our system engineers, and you know, we had this contest. Not really a contest, it was sort of like a poll to say, well, what's his haircut going to be for the landing? And the Mohawk thing won. And he actually kind of grooves on the Mohawk look, so he got a lot of attention for that. You'll see that Fred and I are sitting there together, and I'm looking kind of worried. That's because I just noticed one of the parameters that the sequence, we're like 4 hours before landing, one of the parameters came back. The way it works is we had a couple of parameters that we wanted to change at this particular time in the timeline before landing. And to do those, you had to send a command that changed those, but also set some other things that we wanted to just set to their normal values. And when we do that, we always read out what happened. And when we read that out, some of those things that weren't supposed to change, those numbers that weren't supposed to change, actually changed a little bit, like way down in the 10th decimal place. And I noticed that, reviewing what we just did, and went, oh, shit. That stuff, those numbers weren't supposed to change. And so what followed was about an hour of us trying to make sure that it was okay for those numbers to have tiny little differences out in the 10th decimal place. And it was okay to just, you know, we didn't have to quick build a command and fix that. And it was pretty hair-raising. But, you know, that kind of stuff happens a lot, you know. It's just like the robots that you first guys are building. You know, it's a one-of-a-kind thing, and you get out there on the day that you're going to do the competition, and stuff goes wrong, and you got to fix it on the fly. It's no different than that. That's the EDL team. They were less on TV, but probably just as nervous as those of us in the control room. Those are the folks that did all the simulations and designed the algorithms and set up all the stuff to do the landing. There was a question there. That guy, yeah.
How are the peanuts?
The peanuts are I actually, you know, like just plain peanuts with the little, that come in the little packages, you know, but they were good. You know, it's a tradition at JPL that you eat peanuts that started a long time ago for, you know, originally it was for launches, and then later it became like anytime we did a critical event, and now we have to have peanuts at lunch every day. So it's one of those things that sort of grows on you.
How does the 10th decimal place affect the setting of anything?
Well, it doesn't in this particular case. I mean, there's a few things that the 10th decimal place does matter for. There's a few there's a few parameters on the spacecraft that are, you know, finicky enough that changing something way out there could change the behavior a little bit. But for many things, it didn't matter that much. But we just had to we had to make sure, you know. So we had a lot of. Somebody had the time out there to make jokey pictures and put them on the web, and so this was kind of funny. It made the Mohawk guy famous, and I, you know, have a web page out there somebody made of me because I had long hair. I think because we're all wearing the same shirts, they could just notice our hairstyles. Martine, the guy in the middle, is the guy that actually did all the work on the EDL sequence, you know, kind of the last week before landing, and he didn't get as much press, but he's the real dude. And this is me hoping that everything's really going to work. There's a lot of people that worked on this project. You know, like I said, there's maybe 5,000 people or more spread all over the country that contributed to making this happen. And it cost a lot of money. You know, the U.S. taxpayers cost a lot of money, and NASA's reputation and JPL's reputation. And on top of that, like there's this science mission for, you know, years of exploration on Mars that's all like hanging in the balance. And there's one pitch basically, and it's all hanging on that one roll of the dice. And so a critical event like landing on Mars is always, you know, really anxiety producing. And as I think you heard, it went okay. I was happy after that. I was very happy that it was successful. And it was a big relief to get the information that the thing was down on the ground. Yes?
How far you consider the chances for success?
Let's see. I guess I don't have a good... What would I have said the odds were? I would have said 90%, something like that. I mean, I was pretty confident. The way it sort of works is I know my own area, you know, like I know the GNC stuff and how the EDL stuff works. And so that, I feel really confident about that stuff. But then there's stuff that I don't know that much about, like how do the batteries work? And, you know, what if the IMU got too cold during the, that are uncertain, you know? And that stuff I kind of worry about more, right? The things that I was familiar with, and I think that was true for everybody on the team. The stuff that's their area, man, we got this dialed. We're good, you know. And so, you know, the project manager that's looking at the whole thing has to kind of take everybody's thing and say, I think we're good, you know. But it's still a relief because there's, you know, 60 or 70 pyro devices that have to all work, and all the crazy stuff of this landing system that has to work. These are a couple of the first pictures that we got back. These are thumbnails of the, and I'm 1:30 is when I'm dead. Yeah. These are some. Okay. Well, because we can go into overtime. Okay. But is there a thing on the back of this we have to protect? Okay. Okay. That's great. So these are thumbnails from the HazCams. The HazCams are the little cameras on the front and back of the rover that we use to make sure there aren't rocks and, you know, avoid obstacles and stuff like that. And these are not actually the full pictures, but these are thumbnails, which are compressed versions of them that we can get down pretty quickly. And things worked out super great for us because the orientation that we landed the rover in had the back of the rover looking off in the distance to where the descent stage crashed. And if you actually blink these two pictures back and forth, you can, you know, kind of get rid of the dust on the covers there. And you can see that there's a cloud out there on the horizon. And that cloud is the smoking wreckage of our carefully built and sterilized descent stage at where it went off in the distance and crashed. Yeah.
If it's getting so like dusty on Mars right now, why are you so concerned with keeping dust off of it on Earth?
Because, let's see, there's mechanisms that are on the outside of the rover that are designed to be in a kind of a dirty environment, and they have good seals and stuff on them. But we don't want to get any dust or particles like into the connectors when we assemble the electronics, or any of the mechanisms that are inside the rover where they should be protected. And we don't want to have any biological contaminant stuff that's like we're taking Earth life to Mars on these rovers. We want to minimize as much as we can contaminating Mars with Earth stuff, so that when we go to see if there's life on Mars, it's not like, oh yeah, there's the DNA from Joe, the guy that assembled the Mars rover. So we work really hard to try and, you know, keep things pristine for that reason. There's a couple of the EDL guys. That's Miguel San Martin on the left, who was the guidance and control chief engineer for the entry, descent, and landing, and Adam Selsner, who is the chief engineer of all of the EDL stuff. So those two guys are the guys that came up with the crazy, hang the rover on strings and set it down on the surface, and defended that and convinced everybody that was a better way to do things, a more plausible way to do things than put the rover in a giant beach ball.
It wasn't the same choice, or?
Yeah, it turns out that if you try and land a rover this size, it's the size of a car, it's bigger than a Mini Cooper, try and land that in a beach ball. The beach ball has to be like the size of a football field, and we don't really have material to cover the outside of it that's strong enough. It really doesn't scale to this size rover. So they had to go to a new technology, and there's a lot of complicated trades about how to do it. I mean, one way would be if you could put rockets on the rover and land the thing, kind of like Viking did, but then you have to drive around for the rest of the time with half-full fuel tanks and rockets on the thing. So that's not really good. We could put the rockets on put the rover on top of the descent stage and land the thing like Viking, but then the rover's up on top of a tall thing with tanks, and we have to climb off of there with the rover somehow. And so this system, it turns out, simplifies a lot of things. It lets the descent stage fly and do its flying and can tip and maneuver any direction it needs to. It lets us use the wheels of the rover as the landing gear. It means the rover is ready to go, ready to drive away, essentially right after we land. We don't have to escape from the rockets that landed us. So it ends up simplifying a lot of stuff. Yeah?
Don't you just use the descent stage as like sort of a base, so to speak, where it like opens up a door and the rover rolls out and has like an antenna?
Yeah, I mean, yeah, there may be other ways to do it, but then it's the same sort of a problem. There's an egress problem, and I have to bolt the rover to this thing and then get it loose, and then turns out one of the hardest thing, even for the beach ball lander, was getting the rover's on a thing that's like a lift in a garage of your car, for your car, that lifts it up so you can deploy the wheels, and then there's egress aids, these ramps that fold out that you have to drive over. So it was a lot of the complexity in the MER mission was involved this stuff of getting off of the landing system and tucking up the airbags and all that stuff. And it moves all those technical problems to something that we know really well how to do, which is fly a thing with rockets on it with an IMU on it. I mean, it ended up making it easier. So, and these are the guys that figured all that out. One of the cool things we got was this amazing shot of us descending on the parachute. This is a shot from Mars Reconnaissance Orbiter that was taking as we were floating down on the parachute, and this came to us right after landing. You can see the glasses there. This is a highly enhanced image taken at the party where we were celebrating the landing. There's Steve Sell, one of the powered descent engineer, that's just gotten this on his iPhone that somebody sent him direct from MRO, and he's like, "Check this out!" That was quite a party after landing. So here's the mess we left. You can see. Did somebody have a laser pointer? I can point at some stuff. Maybe it's good enough. There's a guy right here. Excellent. Thank you. Is this? Yeah. How dangerous is? Oh, okay. Yikes. Safety first. Okay. Yeah. If it, let me know if it cuts through the screen. So there's where we actually landed. You can actually see this has sort of been image enhanced, and you can sort of see some disturbance in a whole region here that's from the rocket engines blowing dust off of the surface. There's where the back shell and parachute came down. The heat shield went whump into the ground right there, and that's the mess where the sky crane crashed.
Give us a scale.
It is 600 meters from there to there. So, yeah, a ways, you know, it's a couple of kilometers
Are you going to
away.
drive over there and take pictures of any of the debris?
We engineers would love to go over there and look at the descent stage and take pictures and stuff, but the scientists are like, no, 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 don't go near all that hydrazine and fuel and stuff. It'll contaminate some of the science instruments. We want to be able, the science instruments can detect carbon and are interested in looking for organic things, and the fuel, of course, is, you know, organic material. So we want to try and stay away from that. It may be that on our route we'll get at a place where we can take like a distant, you know, kind of a telephoto picture of some of the hardware. Yeah.
Is there wind? Are you upwind or downwind from the Island Garden?
That's a good question. I don't know the direction of the prevailing winds. There are winds. The atmosphere is very thin there, and so, you know, the hydrazine will, you know, evaporate, you know, relatively quickly. You know, it has a high enough vapor pressure that it'll dissipate pretty quickly. But still, you know, we don't. They're kind of like, and there's probably there. Well, you'll see in a second here.
You must have brought bacteria with you.
I think you're right.
Will they survive the trip, and will they survive on Mars?
That's a very good question. There are specifications for the, you know, total number of biological spores and kind of how much of that stuff we think we can take. Most of the stuff will not get along well on Mars. Out on the surface of Mars, the sunlight, you know, is sort of direct ultraviolet. You know, since the atmosphere is a lot thinner and there's no magnetic field, there's, you know, radiation exposure that you don't get on Earth. The temperature is a lot lower. There's, you know, very little water in the atmosphere. And so all of those things make the vast majority of terrestrial organisms not survive on Mars. And so it sort of self-sterilizes to an extent.
This is bacteria we're talking about.
Right, and there could be, you know, you could probably find some extremophile thing that could survive for some period of time on the surface of Mars. And, you know, yeah, so, I mean, that's about as much as I know about that. We're trying to do the best job that we can at our current level of technology to do things in a sterile way and protect the, you know, how pristine it is, with at the same time, you know, doing Mars exploration. And as I said, material routinely goes back and forth between Earth and Mars. So there have been many opportunities for this much stuff to get transported from Earth to Mars, you know. So it's not like we're the first guys to ever do this. But so here's our parachute and where the parachute and the back shell came down. Here's our lovingly built descent stage and the remnants. Yeah, it's kind of disappointing, but its job is done, right? All of this stuff that we built, the rocket, like the rover is the thing, right? It's the payload. The rest of this stuff is all about get the rover to Mars. When you're done with it, you're done.
Could Mars become like the lower part of the lunar module in the Apollo mission?
Yep.
And appropriately enough? Yeah. That's pretty much.
Yep, we leave it there.
Could we explore the wreckage with like Spirit or Curiosity or Opportunity?
Those rovers don't, the landing sites are like separated the equivalent of continental distances from each other.
Also, didn't Spirit, like, isn't Spirit not really on the way?
Right. Spirit passed on to the great Mars robot place in the sky. It's sad, but it had a long and happy life and did lots of cool stuff. Opportunity's still growing. Yeah.
They all custom designed.
have, and there must have, since they're custom designed, there must have been a lot of testing to make sure they did everything.
Yes, the actual flight processors, the primary flight computers, the RCEs they're called, are a pretty standard space qualified computer called a RAD 750 that is now obsolete and that they no longer have a production line for. It's been replaced with a newer version. They are, I guess I don't have an equivalent modern computer. They're kind of a PowerPC derivative. Let's see, what else can I say about that? A lot of the electronics on the spacecraft is built with field programmable gate arrays. And those things obviously get coded and then tested extensively. And then there's a few other little individual processors. Many of the science instruments have their own little processors in them and stuff like that. And probably most of them are commercial, but they're radiation hardened versions of commercial parts. And typically the rad hard or space qualified versions of those computers and electronics are have less capability. They're kind of like 5 years or 10 years back from the stuff that you're buying in your cell phone or your home computer, just because the radiation hardening process takes a while and sort of calls for larger feature sizes of the actual electronics and stuff. Yeah.
So was all your work then tested on some sort of rig or real actual?
Oh, we have RAD 750s. There's probably 10 or 15 of them in the program that are used in different test beds, and some to test software, and some are in. There's one in a fully built up rover that we can drive around, and so we have those, and then we have software simulations of them and emulations and stuff. So I guess I'm to the point where I show you the movie. There's the heat shield falling away. One of the things we did is we put a high-res camera on the bottom of the rover so we could see the descent, and I'm going to show you that. Yeah?
What is that a picture of in the background, do you know?
In the background, that is a field of sand dunes, which I can show you on the map when we get to a picture. That's the bottom of Gale Crater, and that's the heat shield falling away, and you can see the wiring in the bottom of the heat shield. Sorry, I'm fussing with the microphone. You can see the wiring in the heat shield there for a system that measures how much the heat shield is eroded. This heat shield was a new technology, and we have some instrumentation on it. So now I'm supposed to be done with my talk, and I'm not even halfway through. And I'm going to pop out of there and go over here and show this thing. But if everybody is okay and doesn't need to be somewhere else, then maybe we're okay. We'll just keep going until my voice gives up. So is this running? Yes, it is. So we're looking at the back of the heat shield right now. See, let me just stop every once in a while and point a couple things out. One is, it sort of looked like it was falling away in slow motion, but really Mars' gravity is 1/3 of Earth's gravity, and so it falls away kind of slower than you're used to, than it would on Earth.
Wrist mode is nominal.
Wrist mode is this motion that you're seeing in the picture where we're sort of swinging back and forth. That's us hanging on the bottom of the, under the parachute and swinging back and forth like that. And you'll see there's a point in here where we stop doing that and things suddenly get smooth. And that's where we've dropped out of the back shell. We've cut the parachute loose, and now we're flying. And you'll see the first thing that happens is we'll tip over like that. You'll see the ground kind of slide over. And we tip over to fly away from the parachute so that the parachute doesn't land on top of us by mistake.
Solid range. That filter could vary with the velocity correction of 0.7 meters with time the ground with the radar. Now through the kilometers. The fuel section has separated where we found the ground command zones due to earth occultation as expected. We're using by to prime the Emily engines in preparation for power flight. We're down to 90 meters per second at an altitude of 6.5 kilometers descending.
So we're going to land like right over here. Oh, I didn't. That's a good place. We're going to land like right in here.
This is dispatch for load solution power flow. Director of communications at this time. We may have lost our way.
You can sort of see the sand dunes over here now. Oh, this took us days to get this video down.
We've lost tones from Earth at this time. This is expected. We're continuing on Odyssey telemetry. Ground solution equals minus 10.8 meters, vertical velocity of minus 80.8 meters per second. Start enabled, standing by for batch cell separation.
Tangled Odyssey is still strong.
We are in powered flight.
So now everything's smooth, and we're flying on the rockets.
50 meters per second.
Tangled Odyssey will be
Down to 50 meters per second. 500 meters in altitude.
We're going to land like right in here.
Standing by for Skytrain.
See it blow the dust off the ground?
Nominal altitude error 5.9 meters. We found a nice flat place. We're coming in ready for Skytrain. Down to 10 meters per second. 40 meters altitude.
Almost stopped. That's the wheel dropping into the camera frame there.
Skytrain has started. Descending at about 175 meters per second as expected. Expecting throttle petrol leak.
Tangled Odyssey remains strong.
Tango Delta nominal.
That's the touchdown event.
Yeah. You feel calm, configured, use stable.
And you can see where that's the ground. We're sitting on the ground now. And there's three things that need to happen before we...
Touchdown confirmed. Receive
Is that you?
So the... So we didn't want to jump the gun and declare that we had landed successfully before we, because there's a lot of things can go wrong. If we don't cut the bridle, we've got this rocket-powered thing attached to us that's trying to fly away, right? So, yeah, so there's a lot of bad things that can happen at the end there. So there were three criteria for us declaring officially that we had landed safely. We needed to have the touchdown event, which is Tango Delta nominal, touchdown nominal, which they used Tango Delta so that nobody would say touchdown nominal and everybody would celebrate then. And then we needed to see that the gyros in the rover said that we weren't moving anymore and we're just sitting there seeing, Mars gravity. And then there was another thing, which we were still getting telemetry after we knew the flyaway had already happened, so that the rover computer's still running and that the vehicle's still alive, right? We didn't short something out or die right at touchdown. And so when we had those three things, then the commentator, Al Chen, could declare to the world that we had landed nominally. So that's kind of what you were hearing there.
What's the baud rate to Mars?
It's pretty low. I think we were using 2 kilobits per second, or something like that for late cruise. And then for much of this, we were using tones, which are like a baud rate of 0 or 1 or something. I mean, it's really, we're just shifting the carrier frequency and knowing what carrier frequency we're on, that means a certain thing. So that's a really low thing. And then there's a relay of telemetry through the Odyssey, one of the orbital spacecraft, I don't remember what the data rate for that is, but it's also pretty low. So it's, I don't remember the number. It could be. I mean, there's several different things in the chain, right? There's what's Odyssey's downlink rate to the Earth, and then what's the rate of the UHF from the rover up to Odyssey. So you.
So for these kids who are used to like UVerse, you know, 16
Yeah.
meg per second.
Yeah.
You're talking.
The data rates are really low. I mean, for a lot of spacecraft in flight, we get lower data rates than you get off these first robotic machines, you know? Yeah.
It changes the speed, right? I mean, it gets better
We, we eventually have better capability than that. Yeah, I mean, right now operating the rovers, we don't really need to send that much data up to the spacecraft, but we have a relay system that goes up through, you know, we can send via UHF when Odyssey or MRO flies over, it sends a bunch of data up and then those get relayed down. Yeah.
Everything is slower because you guys, of course, you need to have reliability. You'd rather have a minimum speed which is really low and
Has
about
error.
the same as the maximum
Right.
speed, than a maximum speed which is really high and a minimum speed which is 0.
Yep. And we have lots of, when we design the communications, we set the data rates and stuff so that we always have lots of margin, and it's always going to have error correction codes in it and stuff like that. Yep, absolutely. So I love this picture of us, you know, blowing the dust off with the rockets, and this is a pretty cool picture. That's a self-portrait of the rover that was taken with the camera mast, looking down and then all kind of stitched together. You can see that's the UHF antenna right there. There, it's kind of hard to see the little hexagonal thing, which is a high gain antenna. I like this picture a lot because the mountains back here look like the mountains on Mars should look. You know, it looks like a Chesley Bonsall painting or something.
Steve, that's actually the rim of the crater.
Yes. Absolutely. That is sort of looking back away. That's not Mount Sharp. That's the many kilometers distant crater rim. These right here are the places where our rocket engines were blasting the ground for a while as we hovered just before touchdown, and have scoured out, you know, all the sand and dirt down pretty much to bedrock. And you can see on the deck of the rover here some of those rocks and sand. A little more than some of the scientists expected. Like, hey, there's rocks all over our rover. Well, dude, get used to it. They're going to be there a while. So, I mean, the EDL guys were saying, maybe next time we'll make the bridles a little longer so that we're even farther from the rocket plumes, and you know, so that we get less stuff up on the deck. Yeah, or have a thing that put a rag on the robot arm so you can dust that shit off. Absolutely. And so, you know, here you can see where we've kind of scoured away down to bedrock. Here's a picture that shows Mount Sharp in the distance. Mount Sharp is named for a guy named Bob Sharp, Robert Sharp, who's a geologist, who was one of the guys that trained the Apollo astronauts in geology and, you know, helped them learn how to select good samples and stuff like that. He is a geologist at Caltech, and I got to take a field trip with him once. And he's an amazing, amazing guy. He slept we slept on top of this freezing cold mountain in California. And like I'm in this down sleeping bag and, you know, trying to keep myself warm with hand warmers and stuff. And he's like got this, like a cotton Coleman, like 1950 sleeping bag that he's had since then. And, you know, no Ensolite pad or anything underneath him. He's just kind of sleeping on the hard ground. There's nothing but gristle in that guy. He spent, you know, half of his life out on geology trips and stuff. So amazing, amazing dude that contributed a lot to planetary science. And so the mountain here in the center of Gale Crater was named after him. And you can see here, this is an enhanced version of starting to do our traverse. And those are areas where the rocket plumes came down, and then this whole region that was disturbed by where the dust has been moved around by the rocket engines. We started to do science right away, taking pictures of down in those scours and doing not sampling but imaging of that bedrock. One of the really interesting things that we found right away was a conglomerate. A conglomerate is a sort of rock. It's a sedimentary rock that has rounded pebbles embedded in sand that have been all kind of welded together. And that's diagnostic. I mean, it's a real crisp signature of something that used to be a stream bed. Like you can see those rocks in the pile over here are kind of all the same size. And this not so much, but over here particularly, they've been sorted by something. And what they're sorted by was running water. In a stream bed, when the water's going pretty good, rocks of different sizes fall out of the moving water at different velocities. And so that's why streams, have areas where there's really fine sand in one place and other places where it's rocky, and down in the stream bed where it goes really fast, there are big cobbles. And so this is, the first evidence seen directly on Mars of running liquid water that persisted over a long period of time and was running in streams. Was laid down billions of years ago when Mars had enough atmosphere that liquid water would survive for a long time on the surface. So that was one of the first important discoveries. I love this picture because that is where our tracks start on Mars. So when aliens come and find the rover, they're going to go and they're going to find these and they're going to go, it looks like something fell out of the sky right here. And that's exactly how we got there. Pretty amazing. Oh, and look, here's the rock that we landed on. Right? What's the first thing we do? We land with one wheel on a rock and punch a hole in the wheel. So, yeah, I mean, and of course there's not, we could have landed just 8 inches over that way. In future rovers, we will have a system, like somebody was talking to today, has a system kind of like this that takes pictures of the area around the rover. I'm sorry, let me back up. 2 different things. Future Mars landers will be able to take pictures as they're coming down and look for places where there are rocks and say, oh, I'm about to land in a rock thing or a crater. I'm going to go a little to the left and land in this flat spot over here. Hazard detection and avoidance. And we don't have that for landers. We guided ourselves to a landing point, but buried us someplace. And then the descent stage made sure to set us down very gently on the surface. But there wasn't anything looking out for rocks or a cliff or anything like that. It was just, we had picked a big landing site that we knew was going to be safe all over. The rover, when it drives around on Mars, does have the capability to do that. It can take pictures of the area with stereo cameras, make a map of where the rocks are, decide where there are hazards, and drive someplace 100 yards away, avoiding the hazards and maneuvering around them by taking a series of pictures. So we can do that with the driving stuff. We haven't quite got to where we can do it with the flying, the rover, and touchdown stuff. Yeah.
You're saying if you tell it to go from point A to point B, it'll do that avoidance automatically?
Yes, the software we have up there right now doesn't. It's in the next build of software that's going up in a few months. But we have that capability. The MER rovers had that capability as well. Yeah, you with the blinking.
Did the hole in the wheel affect the performance of the rover?
No, it really doesn't. The wheels on the rover, so we have a full-size rover that we test in a facility at JPL called the Mars Yard, which is a big sand pit with hills and rocks and all kinds of stuff. And the wheels on, let me say first, that its mass is what our real rover's mass is. And so that means that on Earth, it's super heavy, because Mars, the wheels on it get beaten up pretty bad because it's carrying more weight than the Mars rovers one are. And they have cracks and stuff in them, and they've, they understand how, a little puncture in the wheel doesn't really affect their longevity or their ability to drive and stuff like that. So little stuff like that is not really a problem. No, they're not pneumatic. They're made of aluminum.
The wheels are coated with JPL, right, as it drives around.
And you see it in this picture, there's little holes in the wheels. I have a picture later, I think, that shows we have the Morse code for JPL is actually on the wheels, so when we drive it, like leaves JPL. If you know Morse code, so I don't know if there's a decoder for the written up, up there for it, but and we actually use those marks to help measure if the wheels are slipping as we drive and stuff like that. So we have a system called visual odometry that can actually look in the pictures we take and find those and measure them how far we've driven. So here's where we landed. It turns out, well, this picture is stretched so that you can sort of see geology. You can see three different distinct colors that are going on here that are sort of geologically very different. And so the first thing the scientists want to do is drive to a geologically interesting place and sort of learn how to operate their science instruments and figure out, how they can argue who's going to do what first and teach each other how to operate the rover. I mean, these things, when you build a spacecraft or a rover like this, not only is the rover one of a kind, the team that operates the rover is newly formed. And, it's like going out in a ship, you're on a new crew on a submarine and you go out for the first time. The crew has to learn how to work together and learn how to operate all the systems and get everything worked out. Yeah.
So how do they get consensus on what they're going to do? Do they do rock, paper, scissors? Or?
Yeah, there's a lot of that rock, paper, scissors, lizard, Spock.
Yeah.
And there's they have big conferences. Like the planning team might have this many people in it, where they'll have a big conference like this, where the guy will say, well, the chair recognizes the guy from the ChemCam. What would you like to do in the activities tomorrow? And they'd say, well, we want to do this and this and this. And well, can that wait for a day because Joe over here wants to do something with the robot arm that conflicts, and they have a big conference and decide what they're going to do for each day. And then they, once they've decided on that plan, they hand the plan to some engineering folks that put together the actual spacecraft commands that execute that. So this is the first target. We've made it out here somewhere. And then longer term, that little drive that I was just showing you is right up here. Here are those sand dunes and stuff that we were seeing in the Sand Imager pictures. And we're eventually going to drive from there down this way and wind our way up a canyon here. This is looking at the canyons, and I'll show you some other, here's the picture of it right here. So here's the landing site. That place where there's three different things going on is over here somewhere. And we're going to drive down that way, cross over the sand dunes carefully, and then wind our way up through the bottom part of Mount Sharp where there's all these interesting layers and stuff.
And what is that scale, distance?
It is, do I have a scale on there? Here's the scale on here. So that's 5 kilometers. So it's, 5 miles from there to there.
How fast did it go and how long would it take to travel that distance?
It depends on how much we stop along the way. We'll probably stop along the way and do a lot of science. When we're doing cross-country driving, we can go maybe 100 meters a day, something like that. So 10 days for a kilometer, so, sort of. It would, you know, if we drove straight there, we could do it in a month and a half or something like that.
You've got 100 people saying, oh, look at that, let's go.
Yeah, right. But I've got a room full of scientists, you know, that are saying, oh no, I just saw something really interesting, we gotta stop.
Are we stopping?
We'll get to this shiny.
Oh yeah, that's shiny.
Yeah, they may have figured it out by now. But I have a theory myself. So you can see this is sort of where we're going. This is a long distance picture, kind of a telephoto picture of these amazing layers. You know, it's the Grand Canyon all over again. And each of those is a certain era and something being laid down. There was an ocean here and some sediment got deposited and then things changed and the sediment changed. And so different layers got laid down. On this scale, that rock in the distance is kind of the size that our rover is. So it's a big old planet. Science instrument wise, we've got a robot arm on the front of the rover that has all kinds of interesting instruments and stuff on it. It has a camera that is a microscope that you can take pictures up close to stuff, and also will focus at infinity so you can take distant pictures or take pictures of the rover. It has a drill, a hammer drill like you might drill into concrete with, that can actually drill into rocks and get fine samples of powder from rocks. It can scoop up those fine samples. It can run them through little sieves and stuff like that to get particles of a particular size that you want. It can deliver those particles down into a funnel in the top of the rover and pass them into that sand thing that I don't know how it works, that does chemical analysis and mass spectrometry of what the materials the rock are made out of. Let's see, I can't do anything. There's this APXS thing, which is an instrument that uses radiation to measure the composition of rocks, that you can basically set it on a rock and sit there and collect data for a while and get information about the composition. Yeah.
How much power does the Curiosity or the rover use at any given time?
The Curiosity is powered by a thing called an RTG, which is a radioisotope thermonuclear generator. It's basically a little slug of plutonium that's encased in ceramic. There's a couple of them actually. They're cool. They're like, I've seen pictures of them. You can't go anywhere near them, but they're the size of a little film canister or something, an inch square, and they glow red hot if they're just sitting on the table. And they get 5 or 6 of these things and they stack them in a little can. And they wrap them with things like thermocouples or Peltier devices that take that heat and change it into electricity. And the whole package produces a couple of 100 watts. It's the thing that you see, is there a picture? Where's the picture of our rover? Back here somewhere. Well, I'll point it out when we come to it. It's a thing hanging on the back of the rover, and it makes a couple 100 watts. And there's no, you can't. It always produces a couple of 100 watts. If it's making too much, we just dump it overboard as heat. Then we have batteries on board that store it so that we, are charging batteries and stuff overnight, and then we can drive for, do our activities in the day and then charge up some more overnight.
So what's the lifetime?
The actual radioactive stuff in it has a half-life of like 80 years or 90 years. The thing will generate useful power for 5 or 10 years. And it falls off slowly with time, and so we'll be able to operate the rover. That is unlikely to be the limiting lifetime thing for the rover. We're more likely to have something else fail, computer break, something else go wrong.
Is there redundancy in your computer system? So if a computer breaks,
there are 2 redundant computers, and much of the data handling stuff has redundancy. The stuff that powers the rover and stuff are redundant. Most of the science instruments are what we call single string, which is that they're not redundant. though they, sometimes they have some redundant pieces and stuff. Much of the cruise equipment had redundancy of some kind in it. So it's sort of, the redundancies chosen on a case-by-case basis. So here's a kind of an example of the pictures that you can take with that microscope on the arm. You can go from a big picture of a rock up closer, all the way to where you can see the size of individual grains, or these are pits in the basalt. We can also use it, since it's on the arm, to take bitchin' pictures like underneath the rover. Here we've taken the robot arm and are looking and have made a panorama kind of the composite picture of what the rover looks like underneath, which that's pretty groovy picture. There you can see the wheels, and you can see those cutouts are our Morse code stuff. You can see the actuators, motors in here, and there's motors in each wheel. All the wheels are driven. There's a thing called the rocker bogie suspension system, which lets the rover, couples the suspension on the two sides of the rover, and lets the rover drive over large obstacles. You can drive over a rock that is the size of the wheel, actually larger than the wheel, and the rover will just motor right over it. That is yeah.
How's it doing in sand?
It's good in sand too. We're, after the experience with Spirit, of course, we're very careful. The place that we got Spirit stuck was not what you would call sand. It was more like flour. It was like the consistency of flour, or less.
It actually wasn't Spirit, it's just as you said, the sand here. And,
right.
Engineers that have been to Glamis, that didn't advise.
Yeah, and we've taken these things out in the desert and driven them on all kind of, on like beach sand, kind of sand dunes, and they'll drive up incredibly steep slopes and stuff like that. So it's, the mobility system is really, really good, partly because the rover's big, the Murr wheels are about that big, an MSL wheel is like that big. So it's yeah.
Is the sand a little sharper like it's on the moon?
In many places, I'm sure it is. There's a fair amount of aeolian processing of the surface materials of Mars, which means it's blown around by wind. And that is a mechanism that on Mars, rounds things off too, right?
It's not as bad.
The moon is much more like, all of the regolith on the moon are little sharp-edged things that have been formed by meteorite impacts. There's not really much process that makes things round or smooth the sand on the moon. So there's a picture of the top of the camera mast. You can see the HazCams and our high-resolution cameras there. This, I was talking to somebody about cable handling today, and this little ring here, that is a flat cable, a ribbon cable, that is coiled up several wraps, and that grid right there is the cable handling for it, and that's so that we can tilt the camera mast, and those cables, don't get kinked or caught in the machinery or anything. And I was looking at somebody with a challenging cable handling problem on their robot out there. And this thing is an instrument called a ChemCam, and I'm going to try and speed up so that you guys don't drive over. And the ChemCam is really bitching. The ChemCam has a laser that you can blast rock with, and you can then use the little blast to see what the chemical composition of the rocks are. The ChemCam guys think of it like this.
Awesome said that.
It's awesome. Sophie's just fun life, and it's not.
We're gonna win.
Yeah.
So, but this is what it really does. So it makes these tiny little pinhole things. here you can see, you know, we blasted a series of little pits. And this is, you know, it's quite a laser. It's like, it's dumping a gigawatt in a little, you know, few nanoseconds worth of a blast. And it actually does that with a whole series, you know, those are like 100 pulse little blasts. And each one digs its way down a little bit farther, so we can actually tell the difference in the composition of the dust laying on the surface of a rock and stuff down in deeper to the rock, and even see profiles as we go down in through the rock. And this is what the data from the thing actually looks like. It, you know, is a really broad spectra with, you know, stuff from the near infrared all the way down to the ultraviolet. You can, maybe there's not a lot of people that have done spectroscopy with us today, but think of this like a rainbow. Imagine if you took a rainbow and said, how bright is that rainbow at each color? Well, this is a map of that, and how tall the spike is here is how bright the rainbow is at that color. And in this case, you know, our rainbow that you're familiar with goes from like here down to there. And then this is way down in the infrared where bees can like see patterns on flowers and stuff. And this thing is in the infrared where your infrared remote control for your TV works. And it turns out that different elements and different minerals have different signatures like that. And it's sort of a super fancy way of saying what color is this thing I'm looking at. It's not just like our eyeballs can only determine how bright things are at 3 different colors because we have 3 pigments in our eyes. Well, this thing can tell how bright the signal is at many thousands of different frequencies. And so it can do this very precise color determination thing, and different elements have different characteristics. And when you blast the rock, it makes a little puff of plasma, a little bright flame, that you can look at those different elements and recognize them from their patterns.
How far does it do it from?
Several meters, like 10 meters, you know, or something. So one of the cool things about that is you can drive by a rock and go, oh, what's that rock over there? Oh, okay. And go do something that's, you know, pretty far away, and you don't have to actually drive the rover over there, reach the robot, you know, the arm down, and actually touch the rock or you know, interact with it. It's not a remote sensing thing like you can do from orbit. That's what we call remote sensing, is things that you can do from a weather satellite or something like that. But it's not quite in situ. You do have a little bit of a reach because it's this laser thing. It's a really cool instrument.
I'm trying to get a handle on the power consumption of this thing. You said the RTG is delivering a couple hundred watts.
Yep.
But it sounds like driving and analyzing and sending signals and all these things is more than a couple hundred watts.
Yeah, well, we're doing it with a couple hundred watts. But it's a couple hundred watts all day long. And, you know, overnight, the rover, you know, just sits and like curls up in its electric blanket and tries to stay warm because it's down at minus 110 degrees Fahrenheit, you know. So
okay, so
you know,
you're not using power during the
you're
Martian
not,
night.
well, you're using power to run the heaters, but you're not driving, and you're not transmitting with the radios and stuff like that. And I mean, and there's guys whose subsystem is the electrical stuff that worry about the batteries. How big do the batteries have to be? How big does the RTG have to be? What's the power consumption? No, Mr. Cam, you cannot use, you know, 50 watts all the time just to run your computer. You have to use 1 watt, and we'll wake you up when we want to talk with you, you know. So there's lots of, you know, design sort of stuff like that that goes on. Yeah?
What kind of a spectral sensor are you using?
I don't know the details of what's in the ChemCam. And I know that there's a bunch of beam splitter things in there that divide the light up into these, you know, those different regions that you see up there probably each have their own sensor that has its own little prism diffraction grating that splits the thing up, and then there's some detectors there. So I don't know that much about that. So let's see, did I talk about all the science instruments? Pretty much. One other thing that we have is we have a radiation-based thing called DAN, which has a little neutron source that's hung on the bottom of the rover, and it, wherever we drive, is shooting neutrons down into the ground. And with those neutrons, the neutrons can kind of, they interact with hydrogen that's in the rocks, and the hydrogen kind of tells you how much water is bound up in the rocks, or if there were, subsurface water of some kind. And so we can kind of, everywhere we go, tell some information about what's going on with water directly. And that works down to a depth of meters, tens of meters, 10 meters or something. There's a question, yeah?
On the previous slide, you had oxygen showing how high, so that because it's looking at different ions of oxygen.
Different spectral lines of oxygen, probably. And maybe different ionization things of oxygen. But like if you look at a street light, mercury vapor street light with a diffraction grating or with a prism, you'll see or a fluorescent light will do this too, you'll see several different spectral lines that are all coming from mercury vapor. And so there's not just one line for one chemical, there's a pattern for each chemical. And oftentimes it's difficult to take the spectrum and say, oh, it's iron mixed with silicon, mixed with some magnesium. What's the ratio of those things is sort of a complex computer processing thing to figure those things out from the spectrum. But, there's math that lets you do that.
The chem is actually using prisms?
Probably not prisms, they're probably diffraction gratings. But, yeah, it's the same principle of diffraction grating does what a prism you may have seen does, is it splits the light out into, it makes a rainbow from a sunbeam. So here's kind of what's going on with the temperature there. We have a little weather instrument that's hung on the side of the camera mast. And we get up, in the realm of freezing temperatures, your kind of balmy winter, warm Indian summers in the winter kind of temperatures here. And then it gets really cold overnight, gets down to, maybe minus 110, minus 120. Yeah.
Is it year-round on Mars then? Or just
This
for
is
where
the
we
summer
are?
on Mars, where we are right now, kind of near the equator.
Okay.
In the poles of Mars, it gets much colder than this, and in the winter, we'll probably be okay where we are here. It may not ever get above freezing for some part of the year, yeah.
So wait, your ICs, your electronic circuits actually don't like the cold? Because I thought that, they get things better
It's challenging to design things that operate down at these low temperatures, but we test all the stuff, and we, when we go and buy the computer chips and stuff, we say, this thing needs to be space qualified, it needs to work reliably down at 130 degrees below zero.
that you're heating that.
Well, those are the temperatures of the actual environment. The rover doesn't move that much. And it would be great if I had a chart, but I don't, that shows what the temperature inside what we call the warm electronics box is. The inside of the rover doesn't vary this much. It stays, it's probably, we might keep it above freezing, even inside the actual electronics. But that's what's going on. This is what's going on outside on the surface.
The danger is cracking, right?
Yeah, if you go through big temperature swings and you have connectors, yeah, it will shrink and yeah. So, we've started doing some science. You can even do science with the wheels. Here's a place where we drove a wheel up into a place where we had a kind of a sand dune thing, and to see, by looking at these cracks, how strong is the sand, what's the particle size. In the process of doing that, this weird thing showed up. And we don't know what it is. It's not a Mars thing. It's a shiny, weird, shiny thing that somebody noticed in one of the pictures. I think somebody's told me, I don't know if this is true, but that the guy that noticed it was the guy that videotapes all of our stuff. Like, you know, all the pictures of us in the MSA going, hey. Well, there's a guy with a video camera that works for NASA that does that. He made the 7 Minutes of Terror video, and John Beck. Somebody said he's the one that first, hey you guys, what's that thing in the picture? Well, that's one thing we could do. When I left, they hadn't really figured out what it was. They did take a picture of it with the camera that's on the laser, and there's a close-up of it. So it looks like a shrimp, is one possibility.
Isn't there a piece of the plastic from the shield maybe?
Yeah,
Didn't I read that somewhere?
I think they found out yesterday.
Did they, do you know what they said?
I think it was from the rover.
Yeah, it's almost surely from the rover. The speculation that I heard, and y'all have to go on the web and see what the real answer is, but the speculation I heard a couple of days ago when I left was, looked like there were wires, cut off wires hanging off over here, and this looks really a lot like plastic, and there looked like some little fish lips here. So the feeling was that it was probably a splice that somebody had made in a wire, covered with shrink wrap tubing that had been shrunk, which is what makes the little fish lips, and then that needed to be taken back out for some reason and was cut off. And so the wires got cut off, and then it got away from the technician that was doing it and dropped into the rover somehow, or got in some place where it wasn't accessible. You know, I mean, like when you're working on this thing, particularly if you're working on it like after it's been, you know, on the rock, you know, been put on the rocket or something like that, a lot of times it's really hard to get to the place you need to do this work, and you don't want to touch anything else, and you're laying on a platform with you upside down. It's like working under your car or something, and where you don't have much room for your hands or your tools. And so it may have been that he went click and it went beep, and then you couldn't find it, you know. So it's likely something like that. We'll see what the real story is, but a bunch of people have been thinking about it and may have gone, you know, up close with the robot arm and taken a real close picture and can see what it is now. But that sort of stuff happens. There was a bunny rabbit that we found on Mur that was like underneath something, and it blew away, disappeared one day. It's great because it gives the conspiracy guys something to make conspiracies about. And the other kind of cool thing is we've got all kinds of you know, pictures that are coming straight down and being put on the web, and people do stuff like this, which is an afternoon, you know, a balmy afternoon on Mars that they made a panorama themselves and colorized. And so if you're into image processing stuff, you can go on the JPL NASA website and find these raw images pretty much right as they come down and do stuff with them. If you want to try and zoom in and figure out what that thing is before we do, go for it, let us know. So that's all the slides that I had, and be happy to stay as long as you have patience. And
we do have a workshop portion coming. Actually,
okay.
We're running into it right now. So.
Sorry.
Yeah,
Okay. So then let's say this. Let's say class dismissed, and thank you, everybody. And if anybody wants to stay and just ask a question or two, that's fine. If there's any stragglers, but go do the workshop stuff while you're